I'm pretty sure this 3D printed pin is not going to be sufficient to lock the lathe spindle. We should probably make one out of steel. Welcome back to Cloud42. I'm James. Last week, we started working on a spindle lock for the Grizzly G0602 Lathe. We got as far as getting the main body of the lock mechanism milled. Now we need to make the locking pin and the spring detents. So let's get to work. This is the piece of material I'm going to use to make the pin. I'm pretty sure this is 1144 steel, aka stress proof. At least I'm pretty sure that's what I engraved in the end. I always engrave the markings in my materials with my little rotary die grinder and a carbide burr, just because if you write it on with a marker, sooner or later you're going to get some oil on it and it's just going to wipe right off. Now the tip of the pin is a smaller diameter than the main part of the pin, so I'm going to turn that first, and I'm going to turn it just a little bit longer than I need. And the reason I'm going to do that is because I'm going to need to put a tail center in this to support it, and there's not room for me to get this turning tool in all the way to the end of the part when I have the center in place. So I'll go ahead and turn the tip to diameter first, just held here in the collet, and then once I have that down to diameter, I'll put the center in it, I'll extend it out, and we'll turn the rest of the pin. Now I am turning this a little bit longer than I need because I'm going to come back later and cut the center off the end because I don't want a center in the end of the part. Okay, that should be down to the correct diameter for the tip of the pin. So I will grab a small center drill and we'll just put a center in the end here. Lots of oil, take it nice and slow. These center drills, it's really easy to break a tip off if something goes wrong. So making sure you've got the lathe aligned well, taking it nice and easy, using lots of lubricant can keep you out of a lot of trouble. We don't need much of a center. This isn't a very large part. The cutting forces aren't going to be real high, but we do need a center to support it. Then I'll just pull this out to length. Now, technically, you're not supposed to put the center in it in one setup and then change the setup. But with something this thin, it shouldn't be a big deal. And you can see there's no way I was going to get that tool in all the way to the end. I ordered an extended point center just for this project, but it did not arrive in time. Thanks, Amazon. So I'll just take one cut first, and the first thing I want to check is just to make sure that my lathe is turning nice and parallel. And to my chagrin, it most definitely is not. So that's not a big deal. I just need to figure out how much the offset is and then use the set screws to offset my tailstock, half of the diameter distance in the opposite direction, and we should be good. Except that's not exactly how it went. You can see I've switched back over to an imperial micrometer, and the reason I did that is because I have an imperial dial indicator that I was using to shift the center, shift the tailstock. And I did this 4 or 5 times and I was just not getting predictable results. I've got something going on that I can't quite quantify. I need to figure it out. I do know that one of my set screws is jammed and galled in the tailstock, so it's going to need some attention. I think I've got the center as close to on axis as I can, and more importantly, I'm running out of diameter to play with, so I'll take one final pass and we'll just see where we ended up. Now this should be dead on according to the dial indicator, but of course it's not quite exactly dead on. It's close enough. We're tapered by about 35 microns over, what is this, 100 millimeters. I can live with that, but I just don't understand why I can't get that closer. Again, I'm going to have to play with it. The fit though is good, so I think this is going to work regardless. And yes, I did grind this part, and yes, it is very pretty. I'll just clean this up and make it look nice, take out the tool marks. I've got some 400 grit emery here, and we'll just work that back and forth. And yes, you can go ahead and write down in the comments how smart it was for me to put down a paper towel to keep the grit off of the ways of my lathe. Then we'll follow that up with some Scotch-Brite just to buff it out and make it look like we know what we're doing. Now I'm zeroing my DRO on the shoulder here at the base of the tip, because remember we've got some extra length on the end. I don't want to measure from there. So I will just use the DRO and I will measure over from that shoulder at the end of the tip, and then we'll part this off. I'm going to part it off about 0.5 millimeter long so we can come back and clean up that end. And now we'll take this out. We need to swap collets because this is a 3/8 part, and I've turned it down to about 5/16, about 8 millimeter. I'll use a 5/16 inch collet. That seemed to be the best fit. And we'll put it in with the tip out, and we'll take care of shortening the tip first. Once again, I'm zeroing the DRO off of the shoulder because that's the only dimension I know I can trust. I really don't know how long the part is here. We'll move over from that and cut it off at the correct length. Now I could just face this down in multiple passes, but using the parting tool is a little bit quicker. Plus there's always the opportunity for the tool to jam and explode, and that would be entertaining. Unfortunately, that didn't happen today. Make one more facing pass to bring it to the final dimension, and then come in and put a nice chamfer on the end. And by the way, this is the first of many shots in this video that are going to feature soft focus. It's very nice, very artistic. I totally meant to do it that way. And that is the tip complete. Now we can just pull this out and flip it around and put the features on the other end. To finish a part like this to a very precise length, there are several different techniques. If I really cared, I probably would put a collet stop in the collet. I would put the part in, I would face it off, zero my DRO, pull it out, measure it, put it back in against the stop again, and then machine to my final dimension. In this case, I don't care. It's not that precise, so I will just touch the tool off the end. I know how long the part is because I just measured it with calipers, and I'll use my DRO to take a little more than 0.5 millimeter off the end to bring it to its final length. And that will be good enough for this application. If this is off by a few microns, all that means is that the position of the knob on the side of the lathe will be a few microns closer to or further away from the operator. And by the way, throwing tools on the ground is optional. It's a musical option, and it's one that I often take. With the part cut precisely enough to length, we will go ahead and put the hole in to mount the handle. I'm going to start with a spotting drill, just like I always do, just to make sure we're getting this thing started on center. If there's a little pip there and it pushes a flexible drill off center, you can see some wobbling. The spotting drill really helps to avoid that. This is the YG 120 degree spotting drill. Now with a nice spot, I'll come back with the tap drill size for M5, and we'll push this in 10 or 15 millimeters. Start nice and easy just to make sure that it starts centered, and you can really see the wobble. Sometimes you can touch the side of the drill with a finger and you can sort of feel the wobble, but this looks great. That's centered up and started very cleanly. It is a deep enough hole that I want to peck drill it, pull it out and clear the chips occasionally. Actually drilling this with the carriage probably would have been a better choice here because we can move it in and out quicker, but it's not a very deep hole, so the tailstock will work fine. With that cleaned up, we'll bring in a spiral flute tap. We should be able to run this all the way to the bottom of the hole, and it will evacuate the chips out so we don't have to back up to break the chips, and we don't have to worry about them packing in ahead of the tap. And I'm just going to turn the spindle by hand here. Going to make sure that's nice and tight. You really shouldn't put taps in a drill chuck. I know this, but if you get it tight enough on something this small, you get away with it. And we'll run that in until it hits the bottom. And that's the bottom. And we'll back it out. Probably should have put a chamfer on that hole before I tapped it, but I'll go ahead and put one on after I tap it, just to clean it up. The last thing we need to do to this pin is put in the grooves for the spring ball detent. I'll just get this roughly positioned with a scale, just make sure I have enough sticking out that I can reach everything I need to do on here, at least for the first groove. And we'll lock that down. Now these grooves have a square shoulder on one side and a 45-degree shoulder on the other. So we'll start with a parting tool. I'll just use a scale and feel my way to getting that flush with the end of the part. and kind of feel it catching the edge. And when I get it flush, I will set the DRO to 0 and move over to the point where I need to cut the groove. I'll just use a parting tool and we'll go into the correct depth. Now I'm watching the DRO, trying to determine the correct depth here, but there's going to be some tool pressure, so I'll stop a little bit shy, measure, and then adjust my expectations. And I can just get the blades of a caliper in there, see what the diameter is, and then we'll come back and cut it all the rest of the way to depth. Now the base of this groove needs to be 2.7 millimeters wide, and this is a 2 millimeter parting blade, so I'll move over 7/10 of a millimeter and push it in. This won't be exactly right because the tool is going to flex a little bit since we're only cutting on 1/2, but it'll be pretty close. And then I'll bring in a 45-degree chamfer tool, and we'll use this to cut the chamfer on the left-hand side of that groove. I expected this to be pretty easy. I expected I'll just bring in the chamfer tool, I'll cut the chamfer down, try to line up the point, and we'll try to get the chamfer so that it just intersects the flat bottom on the left-hand side of the groove that I cut with the parting blade. And that turned out to be a lot harder than it looked. And looked is the key word. You just can't see anything. So doing this by eye with all the oil and chips in there is very, very difficult. Tried cleaning it off with compressed air and doing it dry, and the technique that I finally settled on was just to feed the dry tool down until it just touched the bottom of the groove, till it just started to polish it, and then traverse to the left, cutting the chamfer. And then I can come in here with the calipers and I can sort of feel the edge there and figure out how wide this is. It should be 2.7 millimeters. You can see we were just under about 2.5, so we'll take a little bit more. The dimensions are not absolutely critical here. It just needs to be pretty close. And that's pretty close. I'll move it over to do the next one. I'm keeping this choked up in the collet chuck just to reduce the stick out. There's a lot of flexibility here, and I want as much rigidity as I can get. Now in this case, I need to measure from the other side of the parting tool, so I'm just touching it off the end. That's not nearly as precise as feeling with a razor blade or a scale, but for this application, it's close enough. And then we'll just repeat all the same operations, just mirror image, and we'll get our second groove there. Now, all the cutting operations raise at least a little bit of a burr, so I'm coming in with a lathe file where I can reach and just lightly touching the edge. I'm not trying to chamfer it. We'll come back with some Scotch-Brite and polish that up. And then we'll bring out the secret weapon, which is the Bright Boy stick. This is a rubberized abrasive that kind of wears into the shape of the part and allows you to polish down in irregular cavities like this. That cleaned up, and that should be good to go. And this is about the point where I realized the focus is not where I thought it was. Yep, the focus is below the part. Yeah. I'll fix that. I mean, we'll switch now from the lovely soft focus to a more crisp aesthetic. That should be the pin complete. It's very shiny. I like shiny. Okay, stop looking at it. Let's go put it together. With all the parts made, we can assemble this. Start by putting the handle on the end of the pin, and I'm just using an M5 set screw here. I had planned on using a longer screw than this, but when I went and looked in my drawer, this is the longest one that I have. I really wanted to get, 10, maybe 12 millimeters of thread inside the plastic handle just so that they'll hold better because it's a soft material, but this is all I had, and it'll work. Don't worry, it's only temporary, unless it works. Now, I have found that these smooth jaw Knipex pliers do a great job of gripping on cylindrical surfaces like this without marring them. Your mileage may vary, but they've worked great for me. Now we just need to put in the ball, and of course the hardest part about this is getting hold of the ball because I have big fingers and it's not very large. It's a 4 millimeter ball, drops right in. And then we'll put the spring in that we harvest from our Automation Direct clicky pen and put on the cap. Now I got a bunch of comments on the last video asking why I didn't just use a set screw to back this up. Well, there's a number of reasons. For one, an M5 set screw is not quite big enough to have a minor diameter that will clear the spring. You really have to oversize it and there wouldn't be much thread left. And an M6 screw is starting to get pretty big. And there's not a lot of length in this hole. So once you start putting a screw in there, you end up with such a short space available for the spring that I didn't really feel like it was practical. I thought it was better to just sketch up this part, send it to the printer. It prints in like a minute and then I can screw it on. And then by changing out this part for a thicker one with a deeper pocket, for example, I could change the fit of the spring if I needed to make some adjustments. So I opted to go this way because I had a 3D printer sitting right here. You absolutely could use a screw, but you're going to be much more limited on the spring. And you can see there that it shot right past the square shoulder on that detent. I was hoping that the square side was going to be much more resistant to pushing past it, and it is if you're not going fast. But like we discussed last time, I may need to go back and make the grooves a little bit deeper, but we'll see. Got my drilling template here, and I did reprint it with the holes in the correct position. I'm checking it here. I already checked it once, and I wrote OK on the side so I'd know which one to use. I just checked it again. Now we can go over and mount this thing on the lathe. I don't really want a bunch of extra speed holes in my lathe headstock, so I want to make sure I get this positioned and that it stays in place while I drill the holes. I'll just use my little digital angle gauge to make sure that I have it squared up. And I thought about just trying to hold this in position while I drilled the holes, but inevitably it's going to move, so I want to clamp it on. Just got a welding F clamp here, and I'll just clamp it around the headstock. There's a lot of stuff on the other side with the ELS and the encoder and the belts, but I did find just enough room to get the screw in there. And we'll use that to hold this in place and use the digital angle gauge to square it up. And actually it's pretty square already, but I'm not one to leave well enough alone, so I'll start tapping it and messing it up, and then I'll have to fix it. And I'll do this a few times, but I'll edit the video so you don't have to watch all of my frustration and all of my fiddling with this. That's pretty good. You should stop there. You should stop. You're just going to make it worse. Yeah, he doesn't listen. There you go. There you go. It's close enough. Just stop. Stop while you're ahead. I'm not absolutely certain that this plastic is going to contain the drill, or that it's not going to shift, or that it's not going to kind of wear into it and wander off. So I will use a transfer punch and put center punch marks in the head. And that'll just give us a little bit of extra insurance. It'll give the drill something to follow to make sure it doesn't try to wander off. Now I'm going to start drilling this with a standard high-speed steel drill. This is 118 degree standard point. And while it is raising some chips, it's not cutting very fast. I'm putting quite a bit of pressure on it. It's kind of an awkward position, but it is working. But I'm going to stop and I'm going to switch to something else, get the template out of the way. I've got these in past the point, so any other drill we bring in should stay nice and centered. I'm switching to a 135 degree split point drill, and as you can see, this is pulling material out of the hole quite a bit faster. Takes a lot less pressure, and we can get those holes complete a lot quicker. And then I'll just bring in an M5 tap and we'll thread the holes. Now this is a spiral point tap because I really don't want to be trying to pull the cast iron dust out through a spiral flute tap. Those things jam up pretty quick and they're easy to break. Since these are through holes and it's not very thick, the spiral point tap will push the swarf through to the inside of the headstock where I can clean it up next time I take the cover off. Just clean those up with a little rotary countersink, wipe this off, and we should be ready to mount the block. To mount this, I'm using 3 M5 socket head cap screws. And the way I laid these out, I've got 2 screws in the front closest to the spindle, and those should be carrying most of the shear load when we actually have the spindle locked and we're putting leverage against it. and then the one on the left just keeps the block from rotating. It's further away, it has more leverage. One screw there should be sufficient, and I really didn't have room to put a screw in the lower left corner without running into the spring or the screws for the spring cap. Get that tightened down and see how it works. That seems to be going all the way in and engaging with the hole. Seems to be lining up. See there, I pulled past the detent again. That's not great. I'm probably going to have to go back and make those deeper. But I'm turning the spindle with my left hand on the pulley on the other end of the headstock, and it does seem to be locking pretty well. The size of that tip is not much smaller than the size of the hole, so this is pretty precise, probably more precise than you would really want it. But, you know, I could, and all the dimensions seem to be pretty controllable, so I went ahead. I could always take it out and turn the tip down. So I've got the spindle locked, and we'll try putting on the chuck here. And I've been experimenting with a strap wrench because there's nothing to hang on to. You can't put a chuck key in this thing. There's nothing to hang on to tighten this down. And the strap wrench does seem to work pretty well. And the lock worked pretty well. And with it locked, we can easily turn the handle without turning the spindle. I think that's going to work. I think we're good here. I'm going to go ahead and put the spindle clamps in here. This is a threaded spindle, so if you run it in reverse or if you slow it down suddenly, the chuck can actually spin off. People have had them spin off and end up on the floor in the middle of a job. That's bad news. Grizzly's solution for that is these little cam clamps that clamp it to the spindle nose so that it can't come off. And just checking for clearance here. I thought I was going to have a little less than 1 millimeter of clearance just based on the CAD drawing, how everything went together. This is a 40 thou pin, about 1 millimeter, and it does clear. So we've got about 1 millimeter of clearance there. And that should be pretty good. I can live with that. Let's go ahead and give this thing a try. We'll put in a collet, lock the spindle, and spin this down. Now the grease in this thing's pretty sticky. I don't know if I might have been better off with the moly lube instead of the red grease, but it'll keep it from, you know, spinning off when I don't expect it. And with the lock, it's no big deal. So put that in, lock that up, unlock it, turn the lathe on, make our cuts. And then when we want to change something, shut the lathe off, lock it, unlock the part, quick and easy, lock it back up, pull the locking pin, and go back to work. I think this is going to work. Now, I had a number of comments on the last video from people who were very afraid that I might forget to unlock this. They wanted a spring that would pop it out so you'd have to hold it in order to keep it engaged. And I really don't want to do that because that's going to make it clumsy because I'll only have one hand for changing chucks. So I promised a couple people in the comments that we would test and see what happens if I leave this thing locked and turn on the spindle. I've got it locked. I've reconsidered my life choices and nothing happens. That's unlocked. That's locked. And as you can see, the VFD really can't do anything about it. It starts up when it's running slow or when it's first starting. There's so little torque until it gets moving that the VFD really can't do anything. All you can really do is just hear the fan starting up. You can see with it unlocked, it is indeed turning. And with it locked, I'll go ahead and turn the speed up a little more just to make sure there's not a difference. And yeah, no, not really. As long as we're here, we might as well try it with all the speed. Turn it all the way up. You can see that runs up to about 1600 RPM. The lathe is on the largest pulley on the spindle, so it has the maximum torque that it's going to have in operation. So this is the worst case scenario. We'll lock it up. And yeah, same thing happens. So we should be good. For those of you who are really concerned, you can go ahead and write down in the comments about why you were still right. There were some concerns that I might actually push it in while it's spinning. I'm not going to do that, but even if you do, the chamfer kicks it out. I've done it kind of slowly rotating by hand, and I don't think it's going to be a problem. However, if it is, then all of you who have been telling me I should get a better lathe might get your wish. Did it work? I don't actually know because I'm recording this before finishing the project because reasons. Assuming that it worked, the CAD model, drawings, and 3D printable files are all available on Patreon. Patrons can download files for all of my projects and get a little peek behind the scenes while helping to support the channel. And if you're already a patron, thank you. You help make all of this possible. If you enjoyed this video, give it a thumbs up and subscribe. And if you didn't like it, tell me why down in the comments. Thank you for watching.